This is video 11, inverse trig graph functions. It is the last video of unit 8. So far this unit, we've dealt with solving all kinds of equations, and now we're going to deal with the inverse trig function graphs. Now, inverse trig is what we've been doing all along. We've been taking the inverse, taking the inverse, taking the inverse, and taking the inverse. But what exactly is going on when you take the inverse? So the first thing we have to talk about is to go back to our discussion on inverse functions. And an inverse function is a function that has had its x and y switched. That is just our basics. And what do we know about this graphically? It means it's reflected over the line y equals x. And before we can do any of this, graphically, we always have to restrict our domain so that our function is one-to-one, because only functions that are one-to-one can have an inverse taken of them. So let's look at these three functions. This is y equals sine x, y equals cosine x, and y equals tangent x. And are any of these functions one-to-one? So we have to go back to the beginning of the year and think about what that meant. To be a function, it has to pass the vertical line test. So if I take a vertical line and I grab hold of it and move it back and forth, all of these three functions pass the vertical line test, thus they are called functions. Oops. Where's my fun line? So if I bring this even down to tangent, it passes the vertical line test. Let me just show you a little clearly. Now, what would happen if I tried to show if it passed the horizontal line test, which would show that it's one-to-one? Well, if I bring this down, you see automatically that it fails the horizontal line test here, all the way up. It fails the horizontal line test all over the place. Not only does tangent fail the horizontal line test, but cosine fails the horizontal line test. And if cosine fails the horizontal line test, you bet sine fails the horizontal line test. Now, if you remember what this means, for every x there is a unique y, and for every y there is a unique x. In order to be one-to-one, that has to happen. And we know there are multiple x's that have the same y value. So negative 3 pi over 2 and pi over 2 both have a y value of 1 for this sine graph, so it's not one-to-one. So the trick is, where can I chop off my graph? So the answer here was no. And this tells you that not the way they are. They are not inverse functions. Not the way they are graphed. So it says give a restriction. Where can I chop it off? So let's pick right here. And how far out do I have to graph on both sides until I run into a horizontal line problem? Well, I can go all the way to negative pi over 2 and all the way to positive pi over 2. And in this zone, sine is going to pass my horizontal line test. So if I get my horizontal line back here, and I move it over here, in this highlighted zone from negative pi over 2, let me just make this a little shorter so it fits my zone. If I move this line up and down, you will see that it always passes the horizontal line test from negative pi over 2 to pi over 2. Okay, so that is a good place. But if I had started at 0 instead, if I had started my line here at 0, you see that it already is always failing the horizontal line test. So I had to cut it off in a place that would make it pass the horizontal line test. So the restriction here is from, let me type here, we could go from negative pi over 2, oops, wrong button, to pi over 2. I'm just going to copy and paste this so I have no issues. And that would include the first quadrant. Now what about cosine? Well, where could I take my highlighter and highlight that? Well, I have to include the first quadrant. That's according to the rules. So here's the first quadrant. And if I went to the left, I wouldn't pass my horizontal line test. It would be doubling up. If I went to the right, I would pass the horizontal line test. I'll get my line here in a minute to check that. And you see that it does indeed pass the horizontal line test all through here. So for cosine, it's not negative pi over 2 to pi over 2. It is 0 to pi. Well, what about for tangent? Well, here's my horizontal line. I'm going to bring it with me. It'll be easiest to check. Well, maybe I'll bring it with me. I can't seem to grab it. I'll make a new one. Where would I restrict it so it would be 1 to 1? So let me make a line right around here and see if I can move this line around so that it is 1 to 1. Well, if I start moving it up here, it seems to pass the whole time. But then down here, it seems to pass the whole time. If I go over here, I seem to pass the whole time. So it's really when I start getting to these parts here that I start having trouble. So where can I restrict it? Include the first quadrant. Would this work? Just bring it up and down? Yes, this would work. Now what would happen if I brought it from 0 to here? Does this even pass? This one passes too. So which one do we go with? Well, we're going to go with the one that does the left and the right and looks most like sine. And there's a reason for that. That's because the inverse will be continuous rather than discontinuous. So we are going to actually use this version. Although there is a second version from 0 to pi, just like cosine, we don't tend to use this one. We use from negative pi over 2 to pi over 2. Okay, going on to the next one. It says, now that we have cut off the domains, we can graph their inverses. And so here we're going to do just sine, and then you're going to do the cosine and trig one on your own. So the first thing is, what is the actual sine values? Well, what is the sine of negative pi over 2? Well, if you know your reference, negative pi over 2 is negative 90 degrees. And what is the sine at negative 90 degrees? Why, that is negative 1. What is the sine of 0? That's just 0. And the sine of pi over 2 is like the sine of 90, and that is 1. Now it says, using your table in part A to construct the table for part B here, inverse. Now if you remember, I started the video saying inverse, you switch x and y. So what was in our y column now goes into our x column. So our x column becomes negative 1, and then 0, and then 1. On the other hand, our y column becomes negative pi over 2, and then it becomes 0, and then it becomes pi over 2. So now we have a set of points to graph. So if we're going to graph this way, now remember negative pi over 2 is going to be negative 1.57, and pi over 2 is positive 1.57, and that's just from typing pi divided by 2 into the calculator, or 3.145 by 2. So we're going to plot this. So our x value, let me get something that's not a highlighter. Our x value is negative 1, and our y value is negative 1.57. So let's go here. Then we go to 0, 0. And then we go to 1 and 1.57. Now normally, you may, in my experience, this scale is always done in pi's over 2's as opposed to being done in integers. So you can scale this in this direction so you can see that the x and y has been switched. So when you actually graph this, this looks a little bit like the tangent graph when you switch it and graph it like this. If you looked at your calculator, if I quickly look at my calculator, it still has the graph up from the last question that we did. So let me just get to a new page. And if you were to graph, now I want to be in radian mode, so I need to change everything to radians. And I want to change my settings in my graph to radians. And I want to graph the inverse sine. So I'm going to go to Trig, grab the inverse sine of x, and look at it. And it's not there for some reason. I don't know what happened. Just try again. Inverse sine of x. Hit enter. There it is. Look at that small little piece. So if I set my window just to show you, it's going to go, I wanted my x to go from -2 to 2 and count by ones. I'm going to set this to negative pi to pi. Okay, so this is what the inverse sine graph looks like. Going back over to the notes, it says solve the equation equals graphically. So what you can do is you can figure out where is pi over 6 and draw a horizontal line, because this would be y equals on this side and y equals on this side. So where would pi over 6 be? It would be around here, a third of the way up. That's not very helpful because we don't know what that answer is, or do we? It's really saying where is this graph equal to pi over 6? What's the height of the graph when you are, how far over are you when the height of the graph is pi over 6? Now, if you know the relationship between a graph and its inverse, you may be thinking along the right lines. But let's go and double check on the calculator. So if I put up another line and type in pi over 6, and look at the graph, you might be having some ideas. So let's do the intersection function. So that goes to analyze the graph and find the point of intersection somewhere between here and here. And this is the value of pi over 6, 0.52. If you look at the decimal we get, and it's 0.5. So it's x over pi over 6 up. So that point of intersection right here is 0.5 comma pi over 6. Now, how many degrees is pi over 6? If you did the conversion, you would know that pi over 6 is 30 degrees. So what is the connection between sine and 30 degrees and 0.5? You should start to be putting it together a little bit. And if I was to rewrite this as sine to the -1, what goes here is 0.5, and you're looking for the degrees or the radians, which would be pi over 6. So what you're finding, if you were to switch this all around, is you're saying sine of pi over 6 equals 0.5. So that's another way to write the equation. These are equivalent equations. This is the inverse function. This is the regular sine function, but they both have the same numbers in them. So how do you interpret your answer to part D in terms of the original sine function? It's really saying what I just said here. 0.5 is the height of the sine curve at pi over 6. Says state in exact form the value of the sine of inverse of the square root of 3 over 2. So you could do the same thing by putting it on the calculator, or you could say, where is sine equal to the square root of 3 over 2? And we've done a lot with that this time. And that means what angle has a sine value of square root of 3 over 2? And that would be 60 degrees, which is really, and they want exact form, so it's really pi divided by 3. And that concludes our video, and this concludes all of Unit 8. This is the end of video 10, or 11, I guess. I hope you found everything useful in this unit, and you will have a unit test on Friday.